Welcome to the 14th lecture video for Physics 4C. This week, we tackle the practical, for particle physicists anyway, problems of relativistic dynamics. And we start this task by re-deriving the expressions for momentum and energy to make them consistent with the postulates of special relativity and the Lorentz transformation. We start in logical order by re-deriving the expression for relativistic momentum. Because we will need the expression for relativistic momentum for the re-derivation of kinetic energy formula. We take a slightly different approach from the textbook in considering a semi-relativistic collision picture rather than appealing to the relativistic expression for velocity or appealing to the outdated notion of relativistic mass. With the relativistic momentum expression in hand, and the definition of force as the rate of change of momentum, we recalculate the expression for the kinetic energy resulting from work being done, where the final velocity may be relativistic, that is, approaching speed of light. We look at some consequences and suggestions of the resulting expression. The last segment of this lecture set covers a few miscellaneous related topics, leaving time in the next lecture for the more thorough coverage of energy momentum 4-vector and using the energy momentum 4-vector to analyze collisions and other relativistic interactions. So this is the lecture on derivation of relativistic momentum. And there are a couple different places from which you can get at this new idea. One of them could be the simple recognition that special relativity is paradigm shifting discovery. So fully understanding and internalizing special relativity should make you question all the formulas you have seen, because all the formulas you have seen in mechanics so far didn't include this paradigm shifting idea. So they could have been right by accident, as some formulas were, especially in electromagnetism. And but more often than not, they would be wrong. They would be what we call low speed approximations to the correct expression. And momentum is same. So you are used to seeing that momentum is equal to mass times velocity. And this made the perfect sense. In physics 4a, we even related this to Newton's laws, and you can use Newton's third law to show that momentum is conserved and all that stuff. Now, you can actually, through consideration of a rather simple situation, you can see that this formula cannot really hold anymore. Let me show you, let me present one such simple situation. So let me describe two balls of equal mass, ball A and B. Let me say they are equal mass and they collide elastically. So whenever they collide, the total kinetic energy is conserved. Okay. And I'm going to have them approaching each other at the same speed. Let me call that V0, and bounce from each other. Then you can kind of imagine what they would do. They would approach, bounce, and then bounce out of at the same speed that they came in with. It's elastic collision. So they collide here, and then after the collision, they go back. As simple as we can make it. And just this situation by itself it's not complex enough for us to start questioning this non-relativistic expression. And that would be the case even if we started insisting, oh, this speed is really large. Let's say this is getting to be comparable to speed of light. Even then, setup is just so symmetric that, yeah, if whatever speed they are at, 90% speed of light, 99% of speed of light, they would come, bounce, and then bounce out. Like they're so symmetric that there's no other way it could be. So let me modify it a little bit with a particular goal in mind. My goal in mind is I want to mix. I want to mix an object that can only be described with a relativistic consideration in mind with another object that's moving at low enough speed that I don't need to consider relativity. So that's where this setup is too simplistic. It's lacking something because either they both have to be relativistic or they both have to be non-relativistic. Now, one way I can tweak this interaction to introduce relativity to only one of the two interacting objects is to give one of them a sideways motion. You can imagine me doing that by maybe this is a charged particle, a proton, and I place it in a region of electric field so that as it's moving downward, it's also getting accelerated to the right with electric field. So at some point, it gains a very large transverse or horizontal velocity and momentum. And somehow I still arrange for the collision so that they collide down here. Now, if you imagine that that kind of situation is doable, not just in thought and theory, but in actual practical experiment, then this is the setup that I have designed. So the particle A is coming off from side, and I'm going to say that we have done our best not to change the vertical component of motion. So this is coming in with some relativistic speed, let me call it VA, colliding with a B, and then moving off. At the way the arrangement works out, it should be the same relativistic speed VA. Horizontally, momentum should be conserved, so there's no reason any of the horizontal component of velocity should change. Let me call that V. And vertically, it's gonna come in with some vertical speed. Let me call it VA perpendicular, and it should go out with VA perpendicular. Now, if you think through this setup, I hope something makes you realize that simply saying that this vertical component remains the same as V naught for all values of VA, that becomes untenable. You cannot hold on to that anymore because from geometry, VA is equal to square root of V squared plus VA perpendicular squared. That's just spatial geometry, doesn't involve any special relativity. Geometry still, Euclidean geometry still works in special relativity. You can see that for high enough value of V, if we insist that VA perpendicular will remain as this, then at some point this will exceed the speed of light c, even for value of V that's less than speed of light c. And that's a contradiction. You can't have that. So when particle A is moving at relativistic speed, you are going to have a situation where this perpendicular component of velocity is not going to be equal to this velocity. Now, I would like to still insist that for this situation, that we still hold on to momentum conservation. That is, we still say that that in this interaction, in this momentum conserving interaction, that we can still somehow say that the perpendicular component of A's momentum is equal to the B's momentum incoming. You know what I mean. The magnitudes are the same, but in terms of directions and whatnot, you would have to arrange it. But the magnitudes are the same. And before, with the low speed approximation, this is what we would have said. We would have said For the low speed approximation, we would have said, well, mass times the velocity in that direction, VA perpendicular, is equal to mass times V naught. That I hope it looks familiar. Now, what we are being forced to say is that for relativistic case, this particular expression can no longer hold, because at high enough speeds of VA, this equality won't hold anymore. So, so we need to figure out, okay, then what modification do we need to make in order to make this work? Let me make this a suggestion. I'm going to suggest that what we need is a change to the expression for momentum. So what we are still going to hold on to is we are going to hold on to the idea of conservation of momentum, that for this collision to work out and all the symmetries to be observed, what we do need to hold on to is that this perpendicular component of momentum for A is still equally magnitude to the momentum for B, so that after they collide and they bounce, the net momentum hasn't changed. What I am willing to reconsider is that this is the expression for momentum. Now for the low speed side, I'll just keep to that. I don't have to change that. But for the relativistic speed side, I need to include a possibility for this expression not quite being right. So what I'm going to do is, in order to say these two sides are equal to each other, I'm going to say, all right, there should be some function that describes how my momentum needs to be changed. And this function is going to be function of speed VA. That seems reasonable to me, just because that's the parameter that determines if we are in a relativistic case or not. So this is the only thing we are assuming, that we have some kind of relativistic expression, and our goal in the next 5 minutes or so is figuring out what this expression is. Now, I do need to bring in an additional tool, because if you're simply looking at this picture, like I've done all I can, like I don't know what else I can do. I can use the principle of relativity, in that if this is an interaction that takes place, I can analyze it from a point of view of an observer who's moving to the right at speed v. From the point of view of that observer, it's still the same interaction, but some of the parameters will change in a way that helps me get at what this modification to relativistic momentum is. So let me draw out a picture for what that looks like. So if this observer is moving to right at speed v, same v as the horizontal component of A's velocity, then what I will have is, so in that observer's view down here, A will be just coming down at some speed VA perpendicular prime. This is my frame S prime. And after the collision, it'll bounce back at the same speed, VA perpendicular prime. And now ball B will look like it's approaching the observer at speed V horizontally. So the ball B should look like this. It'll collide with the A here, and it'll come in with some speed VB prime, and then bounce out at the same speed VB prime. And vertically, it'll be moving at some speed. I want to call it VB perpendicular prime, because I have a feeling that it's probably not going to be the same as V naught. So as we compare the picture in my initial frame S, and compare it in the new frame S prime, we can see we can glean some information. Now, this is where I actually needed to look up and copy down some formula, because it looks like it involves me changing my reference frame, And as I change my reference frame, the primary quantity I'm interested in is the speeds or the velocities. And the velocity is one thing that I've taken no effort to memorize the transformation rules of. So I need to look it up in the textbook and copy it down properly so that I can use it for this next step of derivation here. So let me go to the relativistic velocity transformation section. And once I'm there, I'll copy down what I need and then finish the derivation here. I do have to say this, going through this exercise made me appreciate these formulas more, which I've been really neglecting because I thought, hey, I'd never use that. I guess one place where I should use it is actually here. So um, so velocity transformations, yeah, so this is the formula. Now I do want to caution you a little bit here, which is that so this gives the formulas for transformation of velocities parallel to the movement of frame, but the velocities that I'm interested in are perpendicular to the movement of the frame. So I will copy down that formula, but just to be mindful that I probably won't be using this one so much. So U parallel is equal to U parallel prime plus V over 1 plus V, that's the speed of the frame, U parallel prime over C squared. The formula I will need more is this one that describes the one of the perpendicular components. I can use the one for y or z. They are basically the same for the particular perpendicular axis. So u perpendicular is equal to u perpendicular prime divided by gamma, again divided by 1 plus v, and I have to be careful here. This is u parallel prime over c squared. Okay, I think that's all the formulas I need. Looking at it here, so it doesn't quite do the thing that I wanted to do because I'm starting out from my S frame and I want to transform my S frame velocities into S prime frame. This is telling me how to transform from primed coordinate velocities to the unprimed velocities. And to get the formula, to get the expression for the primed velocity, so to get the reverse transformation, there's actually two different ways you can go about it. One way is you can just algebraically solve for these. It's not actually that hard. You can just do it. You will see that it works out. Um, Another thing you can do that I find better is you can kind of imagine reversing the primed and unprimed frames. Then really what you are doing is you are changing this V into minus V, because from S prime frame, this S frame is moving to left at speed V. So I can do this simple rewrite. I'm going to just swap the unprimed ones with the prime, and wherever I see V, I'm going to replace it with a minus V. So U parallel prime is equal to U parallel no prime minus V divided by 1 minus V U parallel divided by C squared. And then for the perpendicular component, U perpendicular prime is equal to U perpendicular no prime divided by gamma. With the gamma, there's a factor of V squared, so replacing V with the minus V doesn't change anything, divided by 1 minus VU parallel no prime divided by C squared. So let me use these formulas to transform my velocities and write the transformed version of the velocities here. So, so I'm gonna imagine starting out with this and write out what the transformed perpendicular velocity would be. Using this formula here, it's gonna be the the U perpendicular, that's my VA perpendicular, divided by gamma. And I think I can just use gamma with no notation. My gamma, whenever I write it down, it'll mean 1 over square root of 1 minus V squared over C squared with this V in mind. So divide by gamma, divide by 1 minus same V, and then U parallels, oh, that's a V. So 1 minus V squared over C squared. And I think I can actually simplify this a little bit more, because what I have here is 1 divided by 1 minus V squared over C squared. And that's just the gamma squared. So I have gamma squared times V divided by gamma. So all of that simplifies into gamma VA perpendicular. Oh, okay, so that's my transformed velocity here, going from here to here, just added a factor of, or multiply the factor of gamma. Let me do that for VB perpendicular. I guess, let me write that down here. So I'm transforming this velocity, V naught, into this perpendicular component. And so plug in the numbers. My U perpendicular was V naught, divided by, it's the same gamma, it refers to the speed of the reference frame, divided by 1 minus V. But U parallel in this case is 0. So it's gonna be just what I'm subtracting by is 0. So what I'm dividing by is 1, so I'm not really dividing by anything. So good. So these are the two transformed velocities in my S prime frame that I think will be useful in some sense. Now, if you want to make a sense of these formulas that I've written down, one thing you can do is look at the transformation of the horizontal component of the velocity. If it all works out the way you intuitively expected, then when you transform the horizontal component using this formula, it should reduce down to 0. And I think you will see that. And here, the horizontal component should work out to be V. So with that, I can write down my relativistic momentum conservation expression in two different ways. I've already written one expression. This is in frame S. And I can write a similar expression, but in frame S prime. So in frame S prime, what I ought to have is I have this A that's coming in and colliding and going out. So on the left-hand side, I should have M VA perpendicular prime, and this is moving at slow enough speed that I can treat it non-relativistically, leave it alone. And on the right-hand side, for the expression of the momentum of B, I should treat that relativistically, meaning I should have an expression for this, some modification factor that depends on VB times mass times the perpendicular component of velocity, VB perpendicular prime. And I can simplify this expression quite a bit by recognizing one from symmetry. This VB prime should be equal to VA. I think if it's any other way, it doesn't make sense, because you can almost kind of imagine taking this picture, rotating it around, and you would get the picture down here. So from symmetry, these two should have the same magnitude. So this function, f of VA and f of VB, it's the same function of same parameter. I'll just settle on VA. So that's one. And the left-hand side, let me plug in this expression here. So it's m times this quantity here, gamma VA perpendicular is equal to F times M, and VB prime was V naught divided by gamma. Okay, let me just erase the stuff down here to make a little more room for my remaining algebra. So let me look at these two equations and see if I can simplify it somehow. Equation 1 and equation 2. See if I can simplify it somehow. And my goal really is to solve for this unknown modification factor that we somehow need to make momentum work right in relativistic conditions. So so let me write down clean version of these equations, canceling out things that I can cancel out, masses I can just cancel out. So, and I'll just write f as just f, function of speed, and canceled out. So VA perpendicular is equal to V naught to masses canceled out. And let me collect the gamma on the same side. So I'm going to collect the gamma from the right-hand side to the left-hand side. So gamma squared VA perpendicular is equal to F V naught. Okay, I guess I can just to do what? Linear combination, divide top by bottom. Many different ways of simplifying this expression. Whichever way you do it, it turns out to be numerator, the modification function, divided by the denominator, gamma squared, is equal to 1 over the modification function. And what I did was in the process, canceled out these variables. So what you finally end up with is this. The function that you have to modify with of VA squared is equal to gamma squared, or that this function that you have to modify with is gamma. And there's a bit of thing that I'm kind of hand waving, not addressing quite thoroughly, is that so what I want to say is momentum is equal to gamma mv. And for that to work, technically, this thing here, instead of being VA, it should be V. And I will chalk that up to the approximations that I'm doing in treating this as non-relativistic, fully non-relativistic, and this as relativistic. And for this comparison to work well, this should be very, very relativistic, and this should be very, very non-relativistic. And all of that really amounts to me saying that this is much less than VA, and I can say V is approximately VA. And at some level, this approximately becomes equal, and and I can justify this leading to this. So this is the derivation of relativistic momentum without really or with minimal assumptions as possible. And the minimal assumptions are, one, that momentum is conserved, that even though special relativity changed a lot of things, the main idea that momentum is conserved, that didn't change. So we are holding on to that. And two, we are continuing to hold on to the transformations derived in special relativity, which were the relativistic velocity transformation rules that I copied earlier and used. So from the idea of conservation of momentum and relativistic velocity transformation, we can figure out that, yeah, momentum does need to have this factor gamma in order for our conservation of momentum to hold in relativistic cases. And that's the new expression for momentum we'll start using from now on, and everything else that we rederive relies on this expression. And if you want to avoid this 30-minute derivation, you can just memorize this and use that. So let me start from here, which is kind of a quick review of what we've covered last week, Lorentz transformation. And this is what Lorentz transformation says. It says that if you imagine two reference frames, and one of the reference frames, the primed one, is moving relative to the other reference frame, which we'll say is at rest, then given a particular position, coordinate in space, we can express that point either with this axis or this set of axes with reference to time. And the Lorentz transformation that we learned last week is the transformation rule that tells you, given the coordinates reference to unprimed axis, what are the coordinates in the primed axis? It says that x prime coordinate is given by x minus beta ct. This you might have guessed. This is what we were calling Galilean transformation. There's a modification here in that there's a gamma factor here, where beta that I wrote here is defined as v over c. That's a speed in unit of c. And gamma is defined as 1 divided by square root of 1 minus beta squared. So the way the position coordinates transform, there's this previously non-existent vector of gamma. The coordinates in the direction perpendicular to the direction of motion of the frame, that's as expected. They don't change. And one of the things that were most surprising is how the time coordinates transform. Before, it used to be that time was just the same. It didn't transform. There was an absolute time. And in special relativity, what we see is that time transforms, goes as ct minus beta x, and there's this gamma factor. So this Lorentz transformation is what we've been covering through last week. And these all these factors that you are not used to seeing in our previous experience with the mechanics, in addition to the fact that it's modifying your transformation laws, it's paradigm shifting, because these formula laws, they address the very underlying fabric of space and time, the kind of the mechanical things, laws of physics that we were talking about before then. They applied in the world where these highlighted bits didn't exist. Now that you have these highlighted bits, it changes the very underlying laws of nature. And this kind of modification, this is not really a, first time you're saying something like this. I think a lot of people who took Physics 4A will remember saying this, which is, so think back to when forces were introduced to you. We introduced Newton's second law. And we said, okay, in Newton's second law, which describes the net force is equal to mass times acceleration. And if you remember a little bit later in Physics 4A, this actually turned out not to be correct. If you had a mass on object that was changing as the function of time, like rocket propulsion, then your textbook will point out eventually that in that scenario where mass is potentially changing, simple mass times acceleration no longer gives you the correct value of force. What will give you the correct expression for force is the rate of change, time derivative of momentum. And given that momentum is equal to mv, you can see that in the situations where mass is constant, then the time derivative of momentum, again, if the mass is constant, it's simply mass times the time derivative of velocity. So you get this back. But you do need to watch out that if your mass is somehow time dependent, then these two expressions won't agree with each other, and the correct expression is the force described as the rate of change of momentum. So this was an example of a correction of a previously accepted formula that you have seen before. And I guess the difference between what you're now seeing with this example that you have seen before is that, this only affects formula for the force. So once you have the force or the formula for the force, then you don't really have to worry about this distinction. With special relativity, what's different is that it's a paradigm changing idea. Basically, all of physics can be divided into two pieces. Around this division, there's the physics before special relativity, or non-relativistic physics. There's physics after special relativity, or relativistic physics. So everything that you had before in non-relativistic physics, basically all the formulas you've had in non-relativistic physics, you have to question it. It might not be correct. It probably very likely is incorrect. So you have to rederive relativistically correct formulas. There are some exceptions because you basically know one set of laws that were already relativistically correct. That one exception is the laws of electrodynamics, or Maxwell's equations. These are relativistically correct. So for equations that you had, like an equation for the electromagnetic force, or what's called the Lorentz force, that's given by this formula. So electromagnetic force is a charge times electric field plus V cross B. All this is relativistically correct and doesn't need to be modified. Not a single change is needed. But aside from that, everything else you've learned, it's a non-relativistic low-speed approximation, and they now need to be corrected. Now, so you might ask, so how do we, where do we start? How do we redrive these formulas? And there are some principles you can lean on. And in fact, I think I used this to redrive one of the formulas earlier. You can rely on this, which is that general principles, for which I can give examples like you have conservation of momentum, which you actually saw me use to rederive an expression for relativistic momentum, or principles like a conservation of energy and principle of relativity, I guess, and mathematical operations, to the extent that they have nothing to do with the physical, or to the sense that just talking about math, like taking derivative, doing integral. So mathematical operations. All these general principles continue to hold. So just because we have to take relativity into account doesn't mean things like a conservation of momentum and conservation of energy has to be overhauled. They still remain and we can still use them. So now what we have to do is we have to take these general principles and modify the specific formulas so that those specific formulas will be consistent with the principle of relativity, mainly the Lorentz transformation. So that's what we need to do. let me just write that out. And that's what we have done with momentum. Some time ago that you see in lectures, I've used these as a guiding principles to rederive an expression for relativistically correct momentum. So pre-relativity, we had this. Mass times velocity gave you the momentum. With relativity, we need this factor of gamma as a function of v, where, reminder, gamma of v is 1 over square root of 1 minus v squared over c squared. So this is the relativistically correct formula for momentum, and you use this with conservation of momentum principles, and everything will work fine now. Now, if we are trying to use conservation of momentum principles with the pre-relativistic momentum formula, then things will break down. But that's what these formulas are for. So what I want to look at and correct in the remaining, I think, 10 minutes or so, is the relativistically correct formula for kinetic energy. And in order to do that, what's useful is to examine the process that we used before. So consider kinetic energy that we derived in from physics 4a. I mean, we had this formula, kinetic energy is equal to 1/2 mv squared, but the formula doesn't really tell you what to do if you're trying to rederive it to be consistent with the relativity. So what you have to do is think back, where does this come from? Well, it came from what we call work kinetic energy theorem, or more specifically, we made this statement: when you perform work on an object, that amount of work you perform will give you a change of energy. And if you set up the situation so that the only energy that can change is the kinetic energy, then there's a change of kinetic energy. Okay. And if you're in the work kinetic energy theorem, we say this is the network. And work is defined as the dot product of force times displacement, and net force gives you net work. That'll give you this. And I guess your textbook, the way OpenStax University Physics Volume 1 textbook does it, they kind of assume this form of kinetic energy and use that to prove this work kinetic energy theorem. But let me do it backward. Let me do it in a way where we are saying this is our beginning place. And we are going to define our kinetic energy to be consistent with this relationship, to be consistent with this kind of conservation of energy idea. So there are some laws of physics that we have to use. We need Newton's second law that says net force is equal to mass times acceleration. So we use the Newton's second law. And we used some things about kinematics that we knew. In this situation, if you're given the force, you're given the displacement, then it's the kind of the situation where if you want to relate some quantity to velocity, the acceleration, displacement, and want to relate to velocity, somehow time is not involved, then it's the kind of situation where v squared formula is useful. V final squared is equal to v initial squared plus 2 times acceleration times the delta x. I guess technically this is a dot product. So that if they're in opposite directions, it's negative. Yeah. So yeah, in this situation, if you set up the simple situation where your initial kinetic energy is 0, then what you had was from that, your final velocity, let me solve for it in terms of this. Final velocity squared divided by 2 is equal to acceleration dot product with delta x. And this is where you can kind of see the connection here. Imagine plugging in it here, then you get mass times acceleration, dot product with the delta x. Hey, I have that here. So I can substitute in v final squared over 2. I get 1 over 2 times mass times v final squared. And if we say this is the expression for kinetic energy, then this relationship holds. And this is our non-relativistic derivation for kinetic energy. So to get the relativistic kinetic energy, basically the steps, what we need to do is we need to go through the same set of steps, minding the principles of relativity and carefully examining if each step of the way each step of the way holds. So let me start out by just trying to calculate my net work. So my net work, we'll say, is force dot product with the delta x. And I guess looking at my previous derivation, so force is a quantity that I would eventually like to not deal with it directly. So I'm imagining this picture here. Imagine a flat ground. I have some mass sitting here that I'm going to say I'm pushing with some force F, and this is starting at speed 0. And at some later time, I'm going to have this mass that's moving with some final speed, some final state. So as I imagine doing that, let me set it up this way. Let me try to set it up so that my the rate of change of velocity, which will be changing from 0 to some final value, let's say this is what I'm trying to keep constant. So, which means I think I'm trying to say I'm going to try to keep the acceleration constant. Yeah, constant acceleration. And in the previous situation, when you had a constant acceleration, you had a constant force, and that really gave a lot of nice situation setup. And what I will tell you is that we don't have that anymore, because the first thing I will tell you is that this relationship that we had before, that's no longer going to hold. You can see here. So if I say force, now I'm going to be super careful and start out with my general expression for force, the rate of change of momentum. And before, when momentum was mv, and I could say, oh, mass is constant, then I could just say, oh, time derivative velocity gives me acceleration, gives me that. I could do that. But now watch. I'm doing time derivative of gamma as a function of v times mv. Now, in this expression, I have two terms that are potentially a function of time. So v will be a function of time with this. And because gamma is a function of v as well, this is also a function of time. So when I take this derivative, I'll need to use product rule. I have a product of two functions to apply derivative to one and then to the other. And whatever it ends up being, what I can say is that it's not going to be equal to gamma over v times m times the time derivative of the velocity. Like, this is the one thing it's not going to be. So when I have constant acceleration, I'm no longer going to have constant force. So as I imagine pushing this block, I'll have a situation where my force will be changing. So that's the very first thing that we have to realize, and that's what we have to handle first. The realization that as we try to do this work at a constant acceleration, our force will no longer be constant. And you've seen me deal with the situations like this before, where so before we would have said, okay, I have this displacement delta x. I'm applying this constant force F. So I say work done is force times the total displacement. And when we can no longer do that, because our applied force will be a function of something else, so it won't be constant, then our approach, as you have seen before and as you will see now, is to take this entire interval and divide it up into tiny little pieces, and divide it up in such a way that we say, okay, I know how to handle this very small interval, small infinitesimal interval dx. And once I know how to handle that, I'll add it all back up. That'll give me the total change. So that's what we are going to start. We are going to start by saying, okay, I don't know how to handle this entire quantity, but I can calculate infinitesimal amount of work done over an infinitesimal interval. And the force at that infinitesimal interval will be the time derivative of the momentum, that product with the dx. So that'll give me the infinitesimal amount of work done. And I will integrate this from some initial condition to the final condition, and that will give me the total amount of work done. And what I want to say is that we will say all this is going to equal the change of kinetic energy from initial to final. So with that idea in head, let's just start substituting things in. So we have this expression for momentum, relativistic momentum. So we'll say, okay, my relativistic momentum is gamma mv. So let's say I'm going to be integrating from some initial condition to a final condition, my time derivative of gamma. And let me make this one-dimensional just so that I don't have to keep writing vector notation stuff. Gamma mv. We'll say the direction of force, velocity change, and displacement, they are all in the same direction, dx. Okay, I probably should simplify this a little bit. The first bit of simplification is, this gamma and v, they actually are related to each other. Gamma is given by 1 over square root of 1 minus v squared over c squared. And, given this relationship, you can actually invert that. And when you invert it, let me just write it down. You can check my math later. V is equal to c times the square root of 1 minus 1 over gamma squared. So because both gamma and v basically stand for one and the same thing, or they are two different ways to represent one quantity, v. So I would like to shrink these two symbols down into one. Now, this is the step where a lot of people will go kind of take the route that turns out to be harder. Because I think a lot of us feel like we have more intuition dealing with the velocity than gamma. So a lot of us will try to rewrite this thing in terms of v and work it through that way. And this is something that I learned working with the special relativity for a long time, that oftentimes the math is a lot easier when you work with the gamma instead of v. So that's what I'm going to do. I'm going to use this expression here to eliminate v and retain gamma. Let's see what we get when we do that. So I'm still integrating from some initial to final condition. Still do this time derivative of, and instead of gamma mv, it'll be gamma m times all of this. C square root of 1 minus 1 over gamma squared. Now, you might feel like that doesn't look any simpler, but watch. I have this factor of gamma here. I can absorb that into the square root. When I do that, what it amounts is I take this, multiply that by gamma squared. So when I do that, the first term becomes gamma squared. Now the second term, it'll be gamma squared times 1 over gamma squared. So this just cancels out. So this expression here, it becomes mc square root of gamma squared minus 1. No fractions, just some square roots that look a little bit intimidating, but I think we can work through it. So yeah, let's see. I feel like this is about a good time to do this time derivative because I have everything in terms of just one variable. So I think it's going to be at least a little bit manageable to do the derivative. So let's say it's still integral from some initial to final condition. MC are both constants, so not affected by the derivative. And so I should, when I take this derivative, I'm going to use the chain rule. So I need the derivative of outside. So, it's this outside is gamma squared minus 1 raised to power 1/2. Use the power rule. So this vector of 1/2 comes down times the derivative or the power that it's raised to is reduced by 1. So it'll be gamma squared minus 1 raised to power of minus 1/2. That's the derivative of outside. Derivative of the inside is going to be 2 gamma. And gamma is that I'm doing derivative with respect to time, and gamma should still be a function of time. So I still need the derivative of the inside, derivative of gamma. That'll be derivative of gamma with respect to time. Okay, I think I'm done with that time derivative, and I still have this dx. And I can do some simplifications. This 2 cancels that out. And, it still kind of looks intimidating. And there's still a bit of a calculus left. And I will say, in the interest of time, I'm going to take a little bit of a shortcut. So, so far, this derivative is with respect to, this integral is with respect to x. And I happen to know that I would rather have integral with respect to gamma. And I'm pretty sure there's a proper way to do this, either with a u substitution or with, I don't know, integration by parts or whatever. I'm going to engage in a bit of a abuse of notation, because what we have is d gamma over dt times dx. And, this kind of looks like a fraction. So if this is the denominator, I can say, dx over dt, and not have dt here. D gamma times dx over dt. And the reason I do like this is I can identify this as v. So with that a bit of an abuse of notation, I can say all of this is a v. Therefore, using this, c times square root of 1 minus 1 over gamma squared. Now, I'm calling this abuse of notation because it is. I'm doing something improper. Please don't do this in your calculus class. Now, I happen to know this gives me the correct answer. And as long as I do this carefully, it doesn't result in a serious error. So let me do that and wrap up this derivation. So now this is the part where you have to be careful. I've deliberately kept limits of integration vague. I've been saying, integral from some initial to final condition. And that's because I kind of want you to do this from the start. So I want you to say, I'm really talking about my gamma as some gamma initial value, and my final value, gamma final, as some gamma final value. And that'll actually fix, I think, so being careful with the limits of integration is what will kind of cover over whatever wrong thing I was introducing with this abuse of notation. So let me finish this up. There was a reason I did that committed a mathematical sin because it really leads to a beautiful simplification. I have mass times c times, let me just write this out, that's gamma divided by square root of gamma squared minus 1, and let me write out that free in terms of that. So it'll be c times square root of 1 minus 1 over gamma squared, and I still have that d gamma. And this is the beautiful simplification. Look at this expression here, and this expression here, I can simplify it by multiplying top and bottom by 1 over gamma. Now you might think that's not simplification at all. I mean, the numerator becomes 1, but the denominator, this is where you will see, absorbing this 1 over gamma in, gamma squared becomes 1, minus this becomes 1 over gamma squared, and square root of that is the same thing as that. So these two cancel out. That's the simplification. Once you've done that, what's remaining are, let me factor out the constant factors. I have mc, so mc squared. Let me write out the integral of, this is the sole integrand, d gamma. So what used to be a very intimidating and challenging integral in terms of gamma, that's not an integral at all. That's just, it's 1. Antiderivative 1 would be gamma. So that gives you this simple answer that the result of this integration is gamma evaluated from gamma initial to gamma final, or it's gamma final minus gamma initial. Now this is where you do have to be a little bit careful. So gamma final, we can say, oh, that's my whatever gamma I end up with. That's my final gamma. Your gamma initial, if you are starting from rest, if you are starting from where the block wasn't moving at all, that v equals 0, that corresponds to gamma equal to 1, according to this formula. So your initial gamma will be 1. So that's our result. The relativistically correct formula for kinetic energy that comes from this amount of work being done is equal to, there's gamma mc squared minus mc squared. And the derivation up above is the derivation for getting here. Now, once you have this result, I hope you will see that that looks unnecessarily complicated, especially in that you have this minus mc squared term. Before, when you're looking at non-relativistic kinetic energy, you had 1/2 mv squared, and looking at it, you wouldn't think like that looks like one thing, and you wouldn't go out looking for something that's either missing from it, or you wouldn't be trying to interpret what the expression means. When you look at this expression, that's where you say, that looks overly complicated, as in you have this gamma mc squared, which, it seems decent, and especially if you compare it to expressions like relativistic momentum of gamma mv, there's a kind of nice symmetry there. They both have one factor of gamma. Looks great. But what's this nonsense? Why are you subtracting off mc squared? And someone with the right kind of imagination might imagine that this point hints at a true nature of kinetic energy. That kinetic energy is not itself one thing, but it's two things. In that, this, let's just give it a name, total energy. This might be one of the two things that kinetic energy is composed of. And the other thing is, in order to get kinetic energy, an object has some total energy that it has, even when you have speed of 0. So this is what you might call rest energy. And what we call kinetic energy is the combination of this total energy and rest energy, mainly rest energy subtracted away from the total energy, so that at V equals 0, you will have 0 kinetic energy. That's what this expression might suggest, and this is the correct interpretation. I have a slightly longer lecture that does go over that, but this is the relativistic expression for kinetic energy, and there's and we use this as a starting point to get to the idea of total energy, and there's more interesting underlying mathematical structure to special relativity that you will see in other lectures. So this is the result we ended this derivation with. And it does come down to, if we didn't follow all of the derivation, it does come down to the similar justification as momentum. The result is a lot simpler than the derivation is, and it's a lot more useful. Now, maybe it doesn't look as simple as this did. So let me try to justify it in 2 ways. Let's see. One is I can show you that the low speed limit of this expression is what you are already familiar with. So I want to take the limit. This is what I want to show. I want to show that limit as velocity goes to 0, or limit as gamma goes to 1 of this expression here, gamma minus 1 mc squared, is somehow surprisingly equal to 1/2 mv squared. Like right now, it doesn't look it, right? Maybe it'll look more like it once I write out what gamma is in terms of v. So let's try that. So if I write out gamma in terms of v, what that looks like is 1 over square root of 1 minus v squared over c squared minus 1 times mc squared. Does that look like equal to that when you take the limit v going to 0? Not quite exactly, right? Because you get kind of an indeterminate expression. So if v was exactly equal to 0, then it's 1 minus 1, 0. Well, if v is exactly 0, 0 is equal to 0, yeah, when v is equal to 0, they are agreeing with each other. But where that leaves you is it's a little bit unsatisfactory. So like, what if v is equal to 1 meter per second? Are they still equivalent to each other? So so you can actually do this the proper way. You can do Taylor polynomial. You can do it the way you would do it in a Math 3b. Let me take a bit of a shortcut. This is a lot better justified than the other shortcut I took. So let me rewrite this into this form, which is also equivalent to it. It's actually the same thing I did over there. Instead of writing it square root whatever, I'm writing it as 1 minus v squared over c squared raised to the power of minus 1/2. People have seen that? Yes? How many? Yes? Right? This is the same thing as what I just erased, right? Now, this is what I want to ask. How many here have seen something called the binomial approximation? This is a very common approximation you can do when you have an expression of this form. 1 plus a small number that's much less than 1 raised to the power of, I guess, n, but it can really be x, because this does not need to be an integer. It can be any real number. It can be a complex number. So when you have an expression of this form, but the binomial approximation is so it's approximately equal to 1 plus x times epsilon. Let me not do x, sorry. Let me just keep it as n. It's weird seeing x that way.
n times E epsilon. And if you want to go further, you can actually go one step further. It would be n times n minus 1 divided by 2 factorial epsilon squared plus, and then it keeps on going. How many people here have seen this? You have? Yeah, if you've seen it, great. If not, you can actually prove this using Taylor polynomial. You just take the Taylor polynomial of this using this as the variable. Good? So the fact I want to use is this portion. I don't really need the second and the further terms. I only need it up to the linear term. So using this binomial approximation, I want to rewrite this into the approximate form in the limit where epsilon, or v squared over c squared, is much less than 1. So in that limit, this is what this parenthesis thing is approximately equal to. It's 1 plus the thing that's on the exponential, minus 1/2 times the thing that's epsilon, that would be minus v squared over c squared, minus v squared over c squared. Fortunately, the minuses cancel, right? And then minus 1. So let me keep the same color, minus 1. Does something cancel? Yeah, these two minuses cancel, ones cancel, right? 1 canceled out by minus 1. So these two cancel somehow, fortunately. And when you imagine taking this, multiplying it to mc squared, the c squared, which you had here and you don't have here, actually cancels out. So you have 1/2 mv squared is equal to 1/2 mv squared. So this expression that we are claiming is true for all values of gamma is also correct as gamma goes to 1. Or correct, it agrees with the low speed approximation that we have been using. Yeah. Okay, so that's one way of justifying it. And there's a principle in physics. It's called the correspondence principle. It's the idea that in physics, even when a newer theory of physics invalidates something that you know now, what you know now is it's not perfect. It's not completely incorrect. The science we are doing now is different from the science, the PHYS that Aristotle was doing. Aristotle didn't do any experiment of any kind. He was just thinking up things in his head. When he was completely wrong, he had no way of knowing that. The kind of science we do now, it's grounded in experiments. Maybe the scope of its application is narrower than what we think it is, but what we know to be true is it's at least true in the range we have tested it. So this is at least correct for low speed applications. So whatever new theory of physics comes along has to still reduce down to this in the limit where we know the correct approximations. So it's called the correspondence principle. It applies to special relativity, applies to quantum mechanics. And whatever new law of physics we discover in the future, it'll continue to apply. Because it makes logical sense, right? What we think are correct now are not just something we made up. It's something we tested against the experiment. So when we have a true world theory of physics, it'll continue to reduce down to the same expression in the range where we already tested it. So anyways, yeah, so it agrees with what we know already in this sense. So that's good. I guess that's all you need in terms of validation. The other thing I want you to mention in connection to this is it's a leap that we are going to make. So when you look at this expression, it should raise a kind of a question. When you look at this, kinetic energy is 1/2 mv squared. You'll be okay just leaving it as it is. All right, good. That's the kinetic energy. We are done. When you look at this expression, it's oddly and maybe even unnecessarily complicated. We are not saying, so actually maybe this will be a little bit clearer if I write it out this way. So I factored out mc squared, gamma minus 1 times mc squared, so maybe you're looking at this as one thing. Let me expand it out. Expand it out, it says this. Relativistic kinetic energy is equal to gamma mc squared minus 1 times mc squared, so that would be just mc squared. So this is the expression for relativistic kinetic energy. It's oddly complicated. We are looking for one thing that's expressed in two terms. It's like, sorry, I'm not good at analogies, so I shouldn't try. But we are looking for one thing. And when you look at this, it's a nice one, tidied up ribbon that you wouldn't look for any missing pieces. This is an expression that invites looking for the missing piece, because it's something that you think is one thing, but it's expressed in two parts. So I'm making a leap here. I'm making a leap to say, maybe the relativistic kinetic energy really isn't really a one thing. Maybe it is actually a difference of two things, where maybe, so before we are used to saying kinetic energy is the entire energy in the absence of potential energy, Like when this is here, right now, in this state, it has zero energy. And once it starts moving, it has non-zero energy. We are used to saying that. But what I'm saying, this form is inviting you to say is that maybe relativistic kinetic energy, that's not the whole thing. Maybe what we want to call the whole thing, whole energy, is this. This is our total energy. And what relativistic kinetic energy is, it's not the whole energy. What kinetic energy really is total energy minus this. Or you could say this, that total energy is equal to kinetic energy. It's one portion of the total energy plus this something else. And in terms of mathematical expressions, it would be this. So the total energy is gamma mc squared is equal to kinetic energy. Let me just write it down as kinetic energy. Kinetic energy plus this is something else, which apparently is mc squared. Yeah? So, I mean, I'm not saying this proves it, but the way kinetic energy can be written in this form invites this kind of thinking, right? That there's some form of energy that we have never previously identified. It's not part of the kinetic energy, because to get to kinetic energy, you have to subtract this out from the total energy. And it's not part of any other form, because so far we haven't introduced any conservative forces, any potential. So this is not really a potential energy, as you would call it. So there's a term to describe what kind of energy this is. This is what, if you took physics 4A with me, what I called rest energy. It's an energy that, well, let's see what it depends on. See, that's a constant of nature. Depends on mass. So it's an energy some object has just because it has mass, just because it exists. So when you work out the numbers, it'll turn out to be quite a bit. Like this tennis ball weighing, I don't know, having mass of 100 grams or so, has more energy than what's released in, I don't know, hydrogen bomb or something. So it's quite a large value. And at least prompted by the expression, we're saying, well, this has some form of energy that's quite large. And you might call this just the fanciful thinking, except for the fact that you see effect of this in nuclear reactions. So when unstable isotope breaks into smaller pieces, you count up all the masses, you see that mass of the daughter nuclei are less than the mass of the mother nucleus. And they gain the kinetic energy. The kinetic energy came from the rest energy of the initial heavier nucleus. So because for a very small amount of mass, it's such a large amount of energy, you don't see the effect of this in most interactions. You don't see it in physical interactions. You don't really see it in chemical reactions. But in nuclear reactions, there's large enough change of energy that you see the mass changing effect of this rest energy being released. But this is our new picture. That's That's kind of a, I don't know, fanciful guess, at least initially. But as we talk about quantum mechanics and give you some numerical examples of nuclear decays, you will see that this is not just a fanciful idea, that is a form of energy. And I guess what it is it's kind of a manifestation of potential energy that represents potential energy involved in nuclear interaction. So you might have seen this popular expression. It's that, it comes up with when people talk about Einstein. You might have seen this popular expression, E equals mc squared. And if you know me, you know that I have a very low opinion of what counts for popular science. Essentially, I trust nothing that's published in popular science magazines and newspapers. It comes down to people writing those don't understand physics. Like, imagine how much education it took to get you to here. People writing those articles have half your level of your science and math education. So they couldn't have possibly understood what they were writing. So I don't trust anything that they write, science-wise. Maybe other things too. But so this taken at face value is wrong. To make it correct, you can do one of two things. You could make it correct by putting in this gamma here, because yes, that is total energy. Gamma mc squared is the energy, including the kinetic energy. You could make that correction, or you could say that rest energy is mc squared. So with those two corrections, that's correct. But I guess usually, within the limited application of that, when you see change of mass that represents change of energy, then sure. But you just have to be careful that the E here is not supposed to be the total energy. It's the rest energy. Yeah. So you are actually going to see this more when we do quantum mechanics, and as we do more examples of collisions and whatnot, you will actually see this more. It turns out mathematically, I guess we might not get to this part. If we get to this part, you will see that the mathematical behavior of total energy, it's much more nicely behaved than the kinetic energy. So you are almost never going to see me trying to work out kinetic energy directly. If some question asks for kinetic energy, it'll almost always be a two-step process. I will first work out the total energy, and then I will figure out the kinetic energy from here, total energy minus the rest energy. That's how I would usually figure that out. So yeah, so that's a relativistic kinetic energy. That's the first correction to the non-relativistic mechanics that you've known. And you can imagine making this correction for everything else you know, to gravity. I guess, is that it? That might be it. It's indication of how little fundamental physics we've taught you. But because the only other fundamental physics we've taught you is electrodynamics, and I just told you that doesn't need to be corrected. And anything like dealing with the things like spring forces, these are not fundamental physics. So, but now that you know about relativity, what you have to approach with is any other piece of physics that you used to know. You have to, the first time you see it again, you have to ask the question, well, what is the relativistically correct version of that? So when you see momentum, you have to ask, what is the relativistically correct version? That's this. When you see kinetic energy, you have to ask, what's the relativistically correct version? And that's this. And I don't know what else, yeah?
Do we have relativistic version of angular momentum?
That's an interesting question. So you have, well, let's just write that down as an example. So you know about angular momentum. Someone other than Gauge, tell me what, so angular momentum, which we use letter L to stand for. Someone other than Gauge, tell me some other things that angular momentum is related to. Radius, okay. So angular momentum is momentum of something spinning, right? So it will be related to angular velocity. Okay, so if you're going that way, we can actually do an analogy to this. We can say angular momentum is the rotational inertia times angular velocity as some kind of vector quantity. All right. So that probably, my first guess would be, okay, that probably won't be relativistically correct. Because here's the thing. When you're looking at omega, just like there's a limit, this is a good point to discuss speed limit. So yeah, so sorry. It's good that this point got brought up. So I mentioned earlier, when you look at the expression gamma, it becomes problematic if beta is greater than 1, right? So because if then gamma becomes imaginary, now if you are in theoretical physics, you will hear physicists talk about like tachyonic particles or tachyonic something. There's some hypothesized stuff that's supposed to be moving faster than the speed of light. But so this is the problem you would run into if you are imagining something like a regular object going from 0 speed to something that's greater than speed of light. Imagine how its energy changes. So gamma starts out at 1. So kinetic energy starts out at 0. Or if you are looking at total energy starts out at mc squared. As beta becomes closer to 1, as it increases, what happens to gamma? Increases, right? And as beta approaches 1, gamma approaches infinity. What that means is for beta to become exactly 1, it'll take infinite amount of energy. So, maybe it's possible, maybe it's impossible to put this on the other side of the speed barrier. But if you want to push it through the normal way, it'll take a literally infinite amount of energy. So that's the best justification I can say for why speed of light is the universal speed limit. It takes an infinite amount of energy to get to, not exceed, but just to get to the speed of light. Yes?
Would time start going backwards?
Yeah, that's something that, yeah. So that's the theoretical physics that I don't want to address, because I'm not qualified. You can read about it on your own. It's not what we cover in lower division physics. They are all speculative. They may be correct. That's one of the features of the tachyonic terms, but comes down to their speculations. There are no experimental support. So based on that, V has a speed limit. So if you are saying momentum was just mv, you would have a hard limit for momentum. Fortunately, momentum is gamma mv. So momentum can actually increase without limit. And we probably want to say something similar for angular momentum. And if we want to say angular momentum is just this, omega will probably have a speed limit that's based on the speed limit of light and just the size of the object. So this is the non-relativistic expression that's probably not going to be correct relativistically. So I want to go through this exercise of trying to guess at what would be the relativistically correct expression. And I will tell you that this is not the only expression involving angular momentum. There's at least 2 more. I know in physics 4a, when I get to rotation, I tell you, it becomes even more important for you to know these things thoroughly, because often knowing one relationship won't be enough. You have to know all of the relationships that involve this quantity, of which there's 2 more.
Position vector cross product linear momentum.
Yeah, that's actually the fundamental definition of angular momentum. R cross P. And because this, people here remember cross product, kinda? You have a sense it's different from dot product, and it gives you a vector back. So the order matters here. This is actually the definition of orbital angular momentum. And momentum, we can write it relativistically correctly. And R, as long as I'm staying in one reference frame, I can probably just keep this as it is. So if we are trying to guess at an expression that's relativistically correct, this is the best bet. Because this is already corrected for, and this probably. But so in this class, we won't deal with anything that's rotating with a relativistic angular momentum, precisely to avoid this. And the last expression is how this is related to torque. So torque is rate of change of angular momentum. So if you're trying to deal with torque in a relativistic situation, it should be based on this somehow. So there's quite a lot of physics and mechanics that we won't get to because we don't have the mathematical tools, we don't have the time. So, so even though this class supposedly has a prerequisite of Math 3C, you will actually see that we don't really use multivariable calculus. You use them more in physics 4B than ever in this class. Just the way it works out. But I just want to leave you with that there, more for your upper division work than work for this class. That this things about special relativity that we are introducing, it's a paradigm changing. That we've done a little bit of correction with the energy and momentum. But what you have to remember is that any other piece of physics you learned before special relativity, when you come across it again, when you come across it again, and you are dealing with a situation where gamma is much greater than 1, or you're dealing with a situation things are moving close to the speed of light, then you have to ask the question, well, what is the relativistic version of that? Let me, by the way, give you some hint on doing one question in your homework set. Because I think in my announcement I said something like, all the questions are easy if you know the right way to do it. Right? Yes. So this is one of those questions where if, or you know, the implied is that some of the questions can be difficult if you try to do it the wrong way. And this is one of those questions where you could try to do it the wrong way and spend a lot of time doing the algebra. Let me give you a quick hint. That's a kind of an algebra hint. So it says, you know, what is the velocity of an electron that has some relativistic momentum? So you say, all right, so the momentum of the electron is gamma mv, right? And the wrong thing to do here is to say, all right, I'm looking for velocity, so I want to solve this for velocity. So you put in gamma in terms of v. You write in, you know, mv over square root of 1 minus v squared over c squared. And then you go through a bunch of more algebra to solve it for v. You can totally do that. You'll get the correct answer. But what I'll tell you now is that there is a way to do it even more quickly than that way. You can save yourself a lot of algebra. If you notice a very simple fact, this is the very simple fact that it took me a long, I'll tell you, it wasn't until I was teaching special relativity for like second or third semester that I realized that. When you take this expression, the ratios of momentum and energy gives you some quantities very simply. Imagine this. I'm going to take momentum, magnitude momentum, divided by the correct factor, divided by, I guess, E divided by C, divided by E divided by C. Then this is gamma mv divided by gamma mc. What this combination does is it cancels out gamma. So you never actually really have to solve for gamma here. Gamma m cancels out, and you get v over c. This is an often underappreciated fact, that if you know momentum and energy, then you can figure out the velocity, you know, as a fractional speed of light, by just simply taking the ratio of them. Now here you run into a slight bit of an issue that you are only given the momentum and you are not given the energy. Well, then it's just one more step. Just one more step of, did I erase that? I erased it. So the thing that I erased, let me rewrite it, is the energy momentum relationship, which says that energy squared is equal to mc squared plus momentum c squared. So if you know momentum of a particle with known mass, then you don't need a gamma or v. You can calculate energy directly from this energy momentum relationship. So here, and this is how I did it in the solution is you can first compute the energy, using this. So I need the energy, which will be square root of electron mass times c squared plus the momentum. That's the number I copied. So in the Wolfram alpha format, it's going to be 2.6 times 10 to minus 21 kilogram meter per second times c squared. Let's see if it understood me correctly first. It's incompatible units. That doesn't sound right. Oh, I know why. All right, so it's telling me that is the energy. So from what I have there, so I take the momentum divided by that energy over c, that ought to give me the, so momentum, which was this, minus 21 kilogram meter per second, divided by energy, gets divided again by c. That'll give me a number as I'll start out with a fraction of speed of light. So it gives me the fraction of speed of light, 0.9945 whatever. Oh wait, is that what it was asking? Oh yeah, it was asking in terms of fraction of speed of light. So 0.99, let's say 45. 0.9945, and let's hope that's the correct answer. Yeah, that's it. So that saves a lot of algebra. So your numbers will be different. It's randomly generated. But the thing I want you to point out is really this relationship between momentum and energy. That rather than writing this out and then doing a bunch of algebra to solve for V, it can be a lot quicker to exploit this relationship. Yeah. Gotcha.
I'm confused about what's the difference between the invariant mass and the mass of a particle, like a general sense of mass.
So you have seen...
It works as kind of mass, but sometimes it's more like a quantity of conservation.
Yeah. So let me put it this way. Let's see. These two phrases refer to the same thing. Both the what I call invariant mass from time to time, and if I simply call something mass, they both mean the same thing. They both refer to the quantity that you are used to referring to with the symbol m. So invariant mass is mass. It's not any different. But the reason I've gotten into habit of saying invariant mass from time to time is because there's this outdated concept of relativistic mass. Relativistic mass, which I will never put down on any class material I have, other than to tell you, don't use that phrase. But if you see somebody referring to relativistic mass, then what they mean is gamma times m. It's a kind of a now defunct or out of favor concept that as something increases in speed, its mass increases. No one uses that description anymore because one, it's conceptually confusing to say mass of something is increasing. So no one working with the special relativity today uses that concept. And two, this is really redundant because only difference between relativistic mass and relativistic energy is that this thing times the factor of c squared. So this is different from energy only by a constant factor. And so this is an unnecessary concept. So that's why it's out of date, out of favor. No one uses it anymore. But so that's why it's crossed out. But the the historical fact is that this had been in use in the past. So sometimes you will see this being referred to from time to time. I think Giancoli actually makes a reference or to somewhere. So whenever somebody says mass, it ought to mean invariant mass. But just in case there's any kind of confusion, if you want to be sure that there's no confusion, you would say invariant mass. But it means the same thing as mass. Okay? That answers the question. Javier, you had a question? No? Okay, any questions?
Well,
yeah.
Kind of. Could you just scroll down? I just wanted to see the last one on there.
This one? Oh, it's the student solution manual. So I guess I don't really advertise it. It is available on OpenStack's website. Like, you know where to find them, right? It only has all the questions. I guess I kind of ignore its existence. So sometimes I assign all the questions, sometimes even I don't really pay attention to it. So, I mean, you are welcome to look at it. So, yes, good. Okay, any other questions? If you haven't looked at the problem set yet, I think for half of you that might be true. Or you haven't worked through to the difficult part yet. If you can finish it tonight, use the late pass to get one more week. And if you have any questions, bring it up on Thursday's class or whatever. Okay? And I guess we can also, I don't know how many late passes you can use in sequence. I'm happy to answer special relativity questions the week after we come back from spring break too. But your homework might have been due before then. Good. Question?
So if we call it invariant mass, it's same as the general mass. In special relativity, there is a conversion between energy and mass.
There is no conversion between energy and mass.
No.
There's a concept of rest energy. Yeah. So there's the idea of rest energy, which is energy that a particle, something has, even when it's at rest. That's this when gamma is equal to 1. So rest energy is equal to mc squared. But I guess the proper way to look at it is mass is a form of energy. So you're not converting between, it's like, you know, you don't talk about conversion of money from your bank account to your wallet. Whether it's in your wallet or in your bank account, it's still your money. You don't talk about converting between them. Mass, so in the context of special relativity, mass is a form of energy. So you don't convert from mass to energy. It's one and the same thing. So in the context of special relativity, that's why in the discussion of conservation, we don't really talk about conservation of mass because mass is not conserved. It's an aspect of total energy. So we talk about the conservation of total energy. And when we are working through dynamics, what we always work with is the relativistic energy. So this is what someone should call relativistic energy. This is the conserved quantity, and this is what you should use in all your calculations. Even when you're asked for kinetic energy, the thing you do is you first calculate this, and then you subtract the rest energy to get the kinetic energy. So this is the most fundamental quantity you would work with. Good? Yes? Questions? Of some sort.
It was about going from joules to electron-volts.
Oh, it's probably somewhere near the end. Yeah, there it is.
It was before this.
Okay. Yeah. Yeah, this is, so to tell you the truth, you can actually do this one by using Wolfram alpha. I mean, you know, I'm not recommending this, but you can actually do it this way. You can type in what is 1 electron volt in joule. And Wolfram alpha will tell you that 1 electron volt is 1.6 times 10 to the minus 19 joule. And it, so, I mean, don't do it that way. So the reason I wrote this up as a separate question is that, so electron volt is, it's one of the kind of, it's close to a natural unit of energy. Especially as we do quantum mechanics, you will see electron volts way more than a joule. Because joule is it's a really unintuitively large amount of energy. Joule was perfectly fine when you had 1 kilogram of mass that you're going to lift by up 1 meter, then you did 10 joules of work. That was perfectly fine. As we start describing microscopic particles like electrons, protons, Joule becomes unreasonably large. So that's why we are introducing a new non-SI unit of energy, electron-volt. And the point of this exercise is for you to have some sort of intuition for electron-volt. And let me say what I want to say and see if that answers some of your question. And electron-volt is kind of what it sounds like. Let me write it out. So 1 electron, and I guess I might have dash, but let me write it this way. 1 electron times volt. That is really the unit of 1 electron volt. Well, what is 1 electron? That's an object, not a, you could have a bunch of things. But I'm multiplying something to a volt, trying to get an energy. So this better be some kind of charge, right? So this is 1 electron charge, or lowercase e that we use for electron charge or elementary charge, times, well, volt is what it sounds like, 1 volt. And you can express this in coulombs, multiply it out. That should give you the answer in joules. Right? Let me try that on Wolfram alpha. I mean, not in the way I just did it, but in the other way. 1 elementary charge times 1 volt. And that should give you some quantity of energy, and that is this many joules, and that is what 1 electron volt is. So I remember the first quantum mechanics class I took, I was asking the professor during a midterm, like, do you have a conversion factor for 1 electron volt to joule? And he says he didn't have to give me one. I didn't understand it then. But this is why he didn't have to give me one, because if you understood how the unit was constructed, you would know that from elementary charge and whatnot. Okay. Does that answer your question?
Yeah, I saw that they were the same because I might have did what you
Yeah. So because it's a charge times, it's literally the charge times the volts. So you get the same number, but the coulomb turns into joule. Yeah, it's not meant to be a difficult question.